Well, real-time, quality, and meshing. So real-time means that you have the result on the spot while scanning. And we talk here about milliseconds and seconds, not minutes or hours. There's also the meshing side, which means that we convert a point cloud into a polygonal model right away. So instead of using billions of points, we use triangles. The main aspect of this one, though, is the quality. And quality here means that it gives you, well, means a set of tools to give you the best possible quality and precision from your device. Now, real-time meshing on its own is pretty big already because, as I said, you can compress data a lot. So instead of billions of points, you're dealing with only millions of triangles. So it's a lot easier to work with. It allows you to average all the scan passes together and have a nice blending of all this. But the main thing is quality here, because it gives you a feedback on how you can improve your model and where you need to add more scan passes. So first of all, laser scanning is a black art. We say that it's a black art because when you scan, or when you've been trained to scan, you might have been taught to scan in a single direction, keeping the laser orientation approximately the same for a single scan pass. Try to be as normal as possible to the surface. Let's say you have a fillet, you want to scan along the fillet, not across it, in order to have a good point density. But it's hard to keep that all in mind while scanning. So it's hard to become a good operator for a laser scanner. So that's why we say that it's a black art. Now, when people are trying to implement laser scanning in their metrology aspect, and they have no clue on the quality of that mesh at the end. They have a mesh, they know that all the areas have been scanned, but they don't know if the mesh was properly done, And typically, when you find out that there's an area that has some issues, you find it when you're analyzing the scan. So you might be back at the office, you don't have access to the part anymore. It might cost a lot to go back there, or the part might not be available. So it's hard to provide feedback on the quality of the scan whilst doing it. Also, when you scan, you don't have feedback on the quality, but you don't have guidance neither on where you should add more data points. It's hard to see with point clouds. Typically, it's hard to see if you have enough point density everywhere to be able to extract all the measurements. So for an operator, it's hard to know in which direction to go and what he should do in order to improve the quality of his scans. So this being said, the quality of the scan and the precision of the scan depends on the know-how of the operator, which means if you have several operators, you'll probably end up with several different results, which is a big problem in metrology, because metrology means that you want to have something that is repeatable and reproducible from one operator to the other one. So in this case, the operator has a great effect if you don't have any feedback on the quality of your mesh or your scan. Now, in Polyworks 2014, we released a three-step approach to transform laser scanning into a systematic and objective metrology solution. So it guides you in order to have better quality of your scans. And let me show you how this works inside Polyworks. So that's Polyworks 2014. Not a big change in the overview if you're familiar with it. And I'll go through a bunch of projects here to show you a different aspect of real-time quality meshing. The first aspect is where you access it. And in this case, I'll be using a Polyworks line scanner simulator in order to use existing data. But it's exactly the same for all laser scanner plugins inside Polyworks. So when I access my laser scan, there's this new section here for the data structure. In the past, in V12 or V11, it used to be point cloud. There was no possibility to create a mesh while scanning. Now in 2014, there's a new data structure, which is the polygonal model. So while scanning, you'll create a mesh. Let me just start with the first scan here. So that's while scanning. Same thing as if you would have a real device. You see the points as you scan, and as soon as you're done with a scan pass, we convert it into a mesh. If I change the display here to show you what it looks like, oops. You see that it's a uniform grid of triangles based on different parameters that we'll see later. So that's the first scan pass, where you have a lot of triangles. If I add another scan pass on top of that, let me switch back to flat. I'll add a second scan pass next to it. So same thing, while scanning, you see the points. As soon as it's done, we convert it into a polygonal model. And when there's overlaps between the scan, we create an average model. And let me show you what it does. So in this area here, there was an overlap. This overlap doesn't exist anymore. There's only one layer of triangles, and the only location where there's an overlap is where you see this little seam line there. That's the only location where there's two layers of triangles. So in the area where there was two scan passes, what we do, I show you this image here, we blend and we create a single surface from these two. And there's already a small misalignment between the scan passes. That's the same with all the devices, just because of the accuracy of the arm or the optical tracker, whatever gives you this. There's always a small misalignments between the scan. We're talking about something really small, of course. But if you want to have something really smooth, it's nice to have a single surface. So where you have overlaps, we create an average model, and we blend it smoothly with the surrounding. Now, if I keep adding more scan passes, I have another scan pass. So if I show you the seam line, then I have more seam line, but that's the only location where I have only two layers of triangles. And the benefit of having several scan passes at the same location means that it's a better or a smoother surface. If you look here, there's only one scan pass. Here, there's two of them. So it's already smoother, just because you have several scan passes and we blend them together. Now, at this point, as I said, you still have the seam line. Those ones, we don't compute them while scanning because it's too computer intensive. It takes a lot of power to do that, and it doesn't worth it at this point. We remove those seam lines when you click Finalize Mesh. That means you're done with your scanning. And you see here, there's no smooth seam line anymore. There's just a blend between the two. Now, if we look at the parameters for, oops, let me keep there. If we look at the properties of the data we did here, under measurement, we see that it's a scan polygonal model. And we have some parameters here. Those of you familiar with IM merge, it's exactly the same parameters. It's a different way to create the polygonal model, but it's the same parameters. So the sampling step the max adjacent and the max angle are there to control the size of the triangles and how we connect the triangles together. For example, if I use something larger, instead of 0.4, I'll use 1, and I'm working in millimeters here, and I click apply, the triangles are bigger. So this polygonal model is fully parametric. You can change the sampling step, change the max adjacent, and other parameters that we'll see in just a second after scanning it. Doesn't mean that you scan with those parameters that you need to keep them. You can change them. Now, at the bottom here, it's also possible to add smoothing and reduce the number of triangles. So if I activate smoothing here to show you what it does, it will get smoother. So it is smoother a little bit. And in this case, I used a low smoothing because I'm doing inspection. I don't want to modify the shape of the model too much. If you don't want to use smoothing at all, you just uncheck it. That's not a big deal. And you have control on the level of smoothing you want to apply on all this. It's also possible to reduce the size of the triangle, reduce the amount of triangles. So on flat surfaces, we'll create larger triangles. And on areas where there's a lot of curvature change, we'll keep more triangles. If I go back here to show you, that's before the reduction. If I apply it, there's less triangles on flat surfaces, more triangles where you have a fillet there. And in this case, there's also a maximum edge length in order to prevent having only large triangles, because for inspection, you want to keep data in order to be able to fit your planes or your entities on it. So that's for the parameters. Now, if I found out that I need to add more scan passes to this, that's not a problem. I just need to go back in my laser scanning mode, and I'll use another scan here. And as soon as I'll click Start Scan, I'll go back in that mode where I have all the seam lines. So we keep working with the original points at all time. So in the background, they are there. They are used to reprocess with the new parameters and with the new points. Let me just show you here. So we're back with the stitching, stitching lines. I'll just make it finish. And I'm done with it. I just need to click Finalize Mesh, and it will reapply the exact same properties as the one for my mesh here, which means the new scan passes that I just added have been smoothed and reduced. Once merged with the original scan passes, they have been smoothed and reduced with the parameters inside the properties of that object. Now, one more thing about this, the default settings can all be configured from the options here. So you have the default sampling step, the max adjacent, and all this. Now, in this case, we did create a polygonal model. That's the real-time meshing part of it. But I told you the best or the biggest portion of it is the quality. That's why we implemented quality metrics in order to give you feedback on the quality of your scan and help you improve it. So let's see those quality metrics. So the first quality metric here is a high scanner to surface normal angle, which means if you, I'll show you what we did in the scan. We did scan using, that's the laser line, we scan using this direction. And this surface are almost normal to the point of view of the scanner, but this one is at an angle. Let's see what happens in this case. that's what we end up with. We end up with a polygonal model where we have gray areas and blue areas. The gray area means that everything's fine, we have data, it was scanned properly. Where we have the blue areas, that means the angle or the point of view of the scanner was not optimal to scan this section of the part. If I show you here, this is the point of view of the scanner. This is the normal of this surface. It's at 90 degrees, so it's good. It's almost normal to it. This one here is at 61 degrees from the point of view. So it's beyond the threshold or the quality threshold. That's why it's flagged in blue on the screen. Now, the reason why we want to show that as a quality issue, it's because there's two main reasons. The first one is that the point spacing is a lot bigger when you're looking at a surface with an angle, which means you don't have as much definition here that you have on top there. So you don't benefit from the full resolution of your device. The second reason why we flag this as a quality error is the fact that when you scan at 0, the signal to noise ratio is really good. But when you get at 60 degrees, the light going back to the camera is not as big, so you don't have a good signal. The signal to noise ratio is a lot smaller. So we flag that as a quality error. Now, in order to fix that, that's really simple. The only thing you need to do is to scan with a better angle. So in this case, normal to that surface. So instead of scanning with a point of view like this, we scan with a point of view closer to be normal to that surface. So if I use that, I rescan on top of blue areas. As I said in the parameters, we will blend them together. And because we now have a good point of view, the blue will disappear. And I told you we average the scan passes. In this case, we have a scan pass with a good scanner orientation and another one with a not so good scanner orientation. So when we blend them together, we add weight. So the one with the good scanner orientation has a lot more weight than the other one. So it gives you a good result at the end, a good quality for your scan. So that's the first metric. Now, if I show you the second one, it's a low density in regards with the curvature of the scan, of the part. Just to show you what we did here again, we did scan this part, which is a car door, using the laser line across the scanner. So it goes, and we went really quickly in there. So the line spacing is dependent on the speed you use to scan the model. So in this case, we go way too fast in this area, so that we don't have a good resolution in that area. Let's see what happened when we scan it. The area is highlighted in yellow. So if we look at this closely, you see there's kind of a tessellated surface, if you want, where we have flat surfaces in this area. So what we do in this case, how we highlight those surfaces or those areas, we fit some kind of a small surface there. And we look at the deviation between that smooth surface and the connection between the points or the laser line. If that distance is bigger than a threshold, that's where we flag this as a quality error. Now to fix this, we'll just add one more scan pass, but we'll add it with a proper scanning direction, which means that the laser line will wrap around the fillet. So it will prevent having a point density that is too small, because the point density around that fillet will be defined by the point spacing on the laser line. So if I add this scan pass in there, there's no yellow anymore, and we did blend both scans together. And again, the one with the good, like the proper point density in this case, has more weight. And by the way, I did not mention it for the first one. You have this new toolbar at the bottom where you can control the quality metrics. So that was the high scanner to surface normal angle. And you see there's a little bit of blue here. That's on edges. But if I can turn it off and on at all time. Same thing for the yellow one, which is this one. And I can control what's the maximum threshold. We defined that 55 and 0.05 millimeters were the good ones. But depending on the type of part you're scanning, maybe you want to have them a little bit tighter or looser. So that was the second quality metric. Now let's look at the third one, the high noise level. And you get a high noise level typically when you switch quickly from a black surface to a shiny surface, or when you have specular reflection where the camera is kind of blinded because the laser reflects directly into the camera. So if I show you that scan, the area where you have noise on it is highlighted in purple here. And the way we measure that is again by fitting some kind of a small surface there, and we evaluate the standard deviation there. If the standard deviation is bigger than a certain threshold, then we highlight this as a quality error again. And the way to fix this one is to delete the area where you have specular reflection or noise and rescan it with proper laser settings or with a different scanner orientation. So I just deleted it. Then I will add another scan pass with different laser settings in this case. And at the end, because we did delete the area where there was noise and rescan it with proper settings, we now have a nice scan. Now, this metric is this one here, high noise level, and you can control the maximum standard deviation. Now, there's 4 metrics. There's another one that is not part of this toolbar. The first 2 metrics here are on by default. This one is not on by default, just because it's a little bit more computer intensive. So on larger scan, it can slow down process. So it's not on by default. That's something you probably want to use from time to time to see if you have noise, but not for after all scan passes. That was the third metric. Now the fourth one. The fourth one will highlight whenever there's something wrong with the last scan pass you did. And by something wrong, I mean that the scan pass is not aligned with the other scan passes. So if I try to scan this, it's working fine for a while. Everything is aligned. And we have the quality matrix along the way. So in this case, it's blue because the normal was not good. Now, by adding more scan passes, we fixed that. We fixed the low point density to define the curvature. But at a certain point, maybe not like while scanning the part, but maybe in between two scanning sessions, for example, you might get an error like this one. The last scan pass is misaligned. Average deviation is 0.338 millimeters. That means after each scan pass, we compare it with what already exists in the project, and we look at the deviation to make sure there's not something or something did not move. And there's different causes. I'll go to that step right after. But you'll get a message like this. You can either delete the scan pass or keep it. Most of the time, you will probably press delete. But in this case, I'll keep it just to show you what happens. So you see here, there's kind of a seam line there, which is the gap between the two scan passes. And that's something that you were not highlighted before. So you ended up trying to analyze the data back at the office, and well, my part did move. I did not scan it with, I did not realign it. So now I have 2 layers of points, and it's cumbersome to fix. Now you have a feedback while scanning that the last scan pass is not aligned properly. You should do something. Now there's different possibilities to explain why this happened. It might be because the device did move. So let's say you're working on a tripod, someone bumped the tripod, you did not notice it, or you pull on the arm and you pull, like you extend it to the full extent of a joint and it did move a little bit. So the device might have moved. Someone might have touched the part. Let's say you were scanning, you go out for lunch or something, you come back, you try to scan, it's not aligned anymore, so someone might have bumped the part or touched it while you were away. And the last one is temperature. So if you are dealing with something really large and you're having, let's say, a temperature issue that's in the building, you start early in the morning, and during the day the temperature increases, you might have an issue with the temperature as well. Now, one more thing. In this case, I did say I want to keep it. If for some reason I don't want to keep it after seeing the result, I can click here. That's a new icon as well. That photo bar is new, but you can delete the last scan pass. Previously, it was not possible to do it. So I deleted it. I'm back to where I was, and I can continue scanning. This same icon can be used as well. Let's say you select another file here. Let's say you did scan the part, but you notice that something went wrong. You did move up. You're not in the field of view. Something was not done properly. You have the visual feedback from the metric as well. But if you want to get rid of that one, just press there. You remove the last scan pass. So that were the 4 quality metrics. So the wrong surface or wrong direction while scanning the part, the low density to define the curvature, the high noise level, and the misaligned scan pass. Also, up to now, we were dealing with a single device position. So we were able to scan what we wanted to scan on the part using one setup. What happens if you need to move the setup? So if you need to scan the full object, so you need to move either the object or the part in order to get all the way around it. That's the next demo. So what I have in this project here, I already scanned the top section of a part using my first setup. In this case, just to show you the 2 setups, that's setup number 1, really simple setup in this case, but from a top view. And I'll need to use this second setup with the bottom view. So same workflow as if you would use a probing device. I don't know if you're familiar with probing device, but let's say you need to move to access another area of the part. you were using move device here, same concept applies here. So I'll click move device. Let's call it position bottom. And the alignment method, if we would have targets, it would be possible to use targets. In this case, it's a little bit weird to do it with simulator, so I won't use targets. I will use another technique where I will best fit the two scans together. So for those of you familiar with Polyworks already, it's the same thing as you used to do an IM-align to realign scans together based on their surfaces. It's not possible to do it inside IM-inspect. So I'll use a custom method here. I'll click OK. And now I'll go and scan in my second device position. Now, if we look here, just to show you, it will prevent you from creating or adding the scan inside the same data object. That's what the move device button does here. It will create a new scanning object. If we would have stayed inside the first one, it would have been possible to add to the existing object. In this case, we're in a new device position, so it will create a new data object. This way, we'll be able to realign the two together. So I'll click Start Scan, and we did speed up scanning here for the simulator in order to make it quick. But we did several scan passes to fully cover the bottom section of it. Now, in this case, you see I did scan some portions of the fixture. So at this point, I probably want to get rid of those, just to ignore them from the best fit, ignore them from the mesh algorithm or the mesh processing. So I'll get rid of these ones. I'll get rid of these ones as well. Oops. And by deleting them, it will prevent the software from meshing them, so it will speed up things as well. In this case, it's not a big portion of the fixture that has been scanned, but if you would have had like the full, a large portion of the table scan, it's nice to remove it before finalizing the mesh. And I'll click Finalize Mesh to finish or stitch everything together. Now, back in my tree view, I have my two data objects. I have scan mesh 1 from the top, scan mesh 2 from the bottom. I now want to align them together. So as I mentioned, there's a new alignment method inside IM-inspect, which used to be only inside IM-inspect, where it's now possible to it used to be only inside IM-align, where we were best fitting data to data. Now it's possible to do it inside IM-inspect. So you specify if you want to pre-align the part using points. Let's say they are far one from another. You specify which data object you want to move and which one will be fixed in the process. So I'll click Start here. It's asking me for the pre-alignment using the points. I'll put them approximately in the same orientation, and I'll pick at least 3 common points. Just as a starting point, same thing as the best fit with a CAD model, where you pick 3 common pairs of points to provide a starting point. So the software will best fit those 3 points, and from this starting point, will perform the final best fit using the surfaces of the part. And I'm done. I'm now best fitted, or the 2 parts are now best fitted together. Now, in this case, yes, the 2 parts are best fitted together, but it's typically nice to end up with only one data object, a single polygonal model that would combine both of them. If you need to provide it to someone else, if you want to analyze it, it's a lot easier if you deal with only one model. So what I can do, I can unify the 2 models together now that they are best fitted. So I can click Create Polygonal Model, and it will be from scanned polygonal data objects. and I will use my 2 meshes in this case. And the meshing parameters will be from the source objects. So I'll click Create, and it will combine the 2 into a single object. And it starts back with the original data points. So it's not using like the 2 meshes as they are right now. We go back to the raw data points in order to blend everything and average everything as if it would be 2 different scan passes. And at the end, you end up with a single object, which is the unification of the 2 other objects. And if I pay attention in the tree view, I now have my mesh, which is the unified model. But I also have a group that is now hidden by default, where I have my 2 original source objects. So those ones are kept in there in order to update everything. And if I look in their properties, they are now considered as source data objects. So they are not used for computation. So if you do a best fit, they are not used. If you do a column map, they are not used. They are not used for any computation except to create that mesh. And that's the one you will now inspect and analyze. And from this point, it's exactly as if you would have scanned it with a single device position or single setup. You can import your CAD, complete your inspection workflow. Now, to go one step further, I told you we keep these objects here in order to be able to update this. And that's the case. And we keep all the links like that in order to be able to use multiple pieces workflow with this inspection workflow, where we have 2 setups, we need to realign them. So I have a full inspection workflow here. If I go under this one, play inspection, so that's a complete inspection job here. I have my CAD model, I have my source data object, I have the mesh. It's the exact same project as before. Let me just hide this for now. The mesh was best fitted to the CAD. We did a color map. We did inspect the cross sections. There's no report here. I could maybe create a quick report. In this case, maybe just a snapshot without the cross sections. And maybe report all the cross sections. Oops. So let's say 1 snapshot for each cross section. So I have my formatted report here with my full snapshot and a snapshot for each of my cross sections. Now, if I want to inspect this, let's say I have hundreds of these parts to inspect. It's fully compatible with the plane inspection workflow. So if I click New Piece, yes, I want to save it. It's asking me for the new piece name, the properties of this piece. Same thing as regular multiple pieces inspection inside Polyworks, either probing, scanning, or a combination of both. And I'll click Create. It's now, in this case, asking me to scan surface data object. And because I was using the line scanner simulator, it's asking me to select the file. But if you would have used a real device, it would have asked you to rescan the surface scanning one, or scan mesh 1. So I'll reselect it, crank arm top. And we did speed up the scanning in this case. So that's the first setup. If I need, I can get rid of the fixtures while scanning. And once I'm done, I click Continue to tell the software I'm done with scanning of the first setup. It's asking me to move to position 2. So position 2 in this case, I could rename it if I want to. Let's keep it the same. So I'll click OK. Continue. Once I'm done with moving the physical part or the device, it's asking me to scan mesh number 2. So I'll select my file in this case. Now I can get rid of the fixture again if I need to. And in this case, I'm removing a little bit more than just the fixture because I already covered that surface with setup number 1, so it doesn't matter if I get rid of a little bit more. I want to make sure I remove the full fixture in this case. And once I'm done, I click Continue. It will go through the full finalization of the mesh, and it will ask me to pick the same points again, or pick 3 pairs of matching points in order to perform the best fit between the 2 polygonal models. So I'll pick common points on both sides. It will best fit them. It will update the mesh, the unified mesh. It will update the color maps, the best fit, the reports, everything. So I'm done with inspection of piece number 2. If I have several pieces like this, just new piece, it's asking me to scan in first setup, move the device, scan in setup number 2, and it updates everything. Now, one thing I did not mention here, well, I mentioned it, but I did not demonstrate it. If we look at the scan, it's a little bit hard with this one. Maybe I could try to create a caliper. Just to show you. Oops. Let's have a look at the thickness of this part here. So it's 15.219. If I change the best fit between my 2 data objects, between my 2 scan mesh, the unified mesh is fully parametric as well. So if I change the parameters, let's say I'll use all the points this time. So it will update the best fit. It will change the relation between my 2 halves of the models. And it will reunify it and update everything. So if I click Apply, not sure how much it will change, but this value will change accordingly. So it's 15.219. If I update my best fit between my 2 meshes, it will update the unified mesh, update the best fit with the CAD model, remeasure or update the caliper as well. So it's now 15.204. So it did not change that much because in this case it's just using all the points instead of a subsample. But let's say you would have changed the way you align them using remeasuring a plane or something, or adding more targets if you use probe targets, it would update everything. So this unified mesh is fully parametric and will update with the change according to the changes you perform. The other one, I don't want to demonstrate it because it's a little bit awkward to see, well, probing without a device, but it's exactly the same if you use targets. Just to show you the model here. In this case, I have spheres that have been glued on the model. If those are my targets and I probe them in the first setup, then I click Move Device. I will realign using targets. It will ask me to probe them in setup number 2, and I'll be able to continue. So it's fully compatible with targets or any other custom alignment methods. Now, going back to the presentation here. So I told you it was a 3-step approach for to improve the quality of your mesh, of your scan data. So in this case, we can say that the 3 steps are to scan the part. So we convert it into a polygonal model. We analyze it with the quality metrics. and we give you feedback with those colors in order for you to enhance your polygonal model and have better quality for your data. Now, as you can imagine, probably it takes a lot of power to compute that real time, but we were able to, well, we had to implement a lot of parallel processing and use the video card to have the render in real time, and try to keep the RAM memory as low as possible to be able to run it on a typical laptop. But at the end, we were able to manage 100 million triangles with only 8 gig of RAM, and all this with real-time display. So just to give you a reference of what this means, if you scan the largest sheet metal part on a car body in white, which is the body side, it's about 88 million triangles with a sampling step or a triangle size, if you want, of 0.25 millimeters. And what's the other one? Yeah, that's it. 88 million triangles with a point spacing of 0.25, which means you can scan half a car with a typical engineering laptop. Now, with these reasons, that's why we say Polyworks 2014 is a laser scanning platform that is metrology grade, because we provide you feedback in order for the operators to have a good quality at the end of their scanning. So better quality from all your operators means that you'll have a better, an increase in your quality and precision of all your scans. And it will also level it will remove the variability between the operators, because you provide them feedback in order to have a good quality mesh everywhere on the part. Also, having the feedback on the screen while doing it, it will speed up the learning curve for new users. So this way they scan, they know right away that they did something wrong that can be improved. So the learning curve to know how to create a better scan is a lot faster.